Welcome back to DeFi Exploits Explained. Today one of the sneakiest bugs in the whole space, and one most developers get wrong, read-only reentrancy. A contract adds a reentrancy guard, feels safe, and still gets drained because a harmless looking view function, the kind that just reads a number, tells a lie at exactly the wrong moment. We'll build a vault, use it to rob a second contract on camera, and then close the hole with a single line. Let's go. Here's the whole idea in one breath. A normal reentrancy guard stops you from calling a function again while it's still running. Good, but it does nothing to a view function, a read-only getter, called in the middle of that same transaction. And here's the catch. Halfway through a withdrawal, a contract's books are only half updated, the ETH has left, but the share count hasn't dropped yet. So a price getter, read at that instant, returns a wrong number. It's not lying on purpose, it's just being asked mid-surgery, and any other protocol that trusts, the price can be robbed. And this is not hypothetical. The read-only reentrancy class was disclosed publicly in 2022, and researchers found it put over $100 million across major protocols at risk. In early 2023, the lending protocol dForce lost around $3.5 million to exactly this, a price read from a curve pool while that pool was mid-operation. Same root cause every time. Someone trusted a view function that was quietly reporting a half-updated state. Let's build the minimal version pool. Here is the trick on one screen, and the numbers make it click. Our vault holds 100 ETH for 100 shares, so a share is worth 1 ETH. The attacker deposits 100 ETH of their own and now owns 100 of 200 shares. Then they withdraw. Watch the order. The vault, Zolot, values their shares 100 ETH and sends that ETH out first before it lowers the share count. So for one instant, mid-withdraw, the vault holds only 100 Ether, but its books still say 200 shares exist. Ask its price right now, and it answers half an ETH per share, half price. And the vault's own sending of Ether is what hands control to the attacker at that exact instant. In that window, the attacker turns to a seller offering vault shares and buys with 25 ETH. The seller innocently asks the vault the price, here's the lie, half, and so hands over 50 shares instead of 25. The withdrawal finishes, the price snaps back to 1, and the attacker redeems those 50 shares for 50 ETH. They paid 25, they got 50. The 25 ETH of profit came straight out of the seller's pocket, all because one view function answered mid-withdrawal. Let's build it in Foundry. Here's the project, a config file, a source folder for our contracts, and a test that runs the attack and checks the result. Everything runs locally on your own machine against no real users and no real money. We start with the skeleton, just the shape, no logic, for 3 contracts. The vault, where people deposit ETH for shares and withdraw them back with the usual reentrancy guard. A seller, which sells vault shares at whatever price the vault reports, and the attacker. Every function has a comment saying what it will do and an empty body. Now we fill them in one contract at a time. First, the vault. Deposit takes your ETH and gives you a fair share of the pool. Withdraw is where the bug lives, and it's all about the order of 3 steps. It works out what your shares are worth, then it burns your shares, then it sends you the ETH, and only afterwards does it lower the total share count. That single line, shrinking the supply after the ETH has already gone out, is the whole vulnerability. And price per share down here is an innocent view, balance divided by shares with no guard on it at all. Remember, the guard only protects withdraw, it never touches this getter. Next, the seller, and this is the victim, it sells vault shares to anyone with ETH. To price them, it does the natural thing. It asks the vault price per share. It completely trusts that number. Divide the ETH you paid by the price, and that's how many shares you get. So if the vault ever reports too low a price, the seller hands out too many shares. It has no idea it's being asked in the middle of a withdrawal. Now the attacker, which ties it together, Kubun deposits ETH to become a normal shareholder, arms a flag, and withdraws. The magic is in receive, the function the vault calls when it sends ETH. Because that call happens mid-withdraw, while the price is temporarily half, the attacker uses that instant to buy cheap shares from the seller at that fake half price. Then the first withdrawal finishes, the price snaps back to normal, and the second withdrawal cashes those cheap shares out at full value. Deposit, withdraw, buy cheap, redeem dear, and the difference is pure profit. Before we run anything, let's read the test. So a green check actually means something. It deploys the vault and the seller and gives an honest provider 100 ETH, who deposits it 100 ETH for 100 shares price 1. The provider hands the seller 50 of those shares to sell, then it builds the attacker aimed at both, funds it with 100 ETH, and calls spoon, the one call that does the whole attack. It logs what the attacker put in, 100, and what it walked out with. And the final line is the real claim: the attacker's balance is now greater than the 100 it started with. If that holds, we made money out of thin air and it came from the seller. Run it. The vault and seller start fair, our shares is worth 1 ETH. Then the attack fires and read the log. Attacker in 100 ETH, attacker out 125, a 25 ETH profit pulled out of the seller with no flash lane and no stolen keys, just a view function answered at the wrong moment. Passing green means the theft worked exactly as designed. So how do we stop it? One line, we add the same reentrancy check to the view function itself. If a withdrawal is in progress, price per share simply refuses to answer and reverts. That's it. Now, when the seller tries to read the price mid-withdraw, the read fails, its whole call fails, and because that call is nested inside the attacker's transaction, the entire attack unwinds. The rule to take away: if a value can be read while your state is half updated, guard the read, not just the write. And here's the test for the fix. Same setup, but now the guarded vault. The key line is expect revert. We're telling Foundry the very next call must fail. Then we run the exact same attack. If the guard does its job, the seller's price read reverts mid-withdraw. That failure bubbles all the way up and pound reverts. This test passes precisely when the attack does not. Same attack, now against the guarded vault. The test expects it to fail, and it does. The moment the seller asks for a price mid-withdraw, the guard trips, the read reverts, and the whole attack rolls back. The seller keeps its shares, nobody is robbed. This test passing means the attack was blocked, one line, and a whole class of drains is closed. And this isn't only a local test. I deployed both vaults to Sepolia, a real public Ethereum testnet, and fired the same attack at each. On top, the vulnerable one. The attack transaction succeeds, and the attacker walks away richer right there on the block explorer for anyone to verify. On the bottom, the guarded one. The exact same attack fails, reverted on-chain. Same code, same attacker. One line of difference between a robbery and a safe protocol. Quick recap: a reentrancy guard protects the function that changes state, but it does nothing for a view read in the same transaction. And halfway through a withdrawal, state is half updated, so that view returns a number that's briefly wrong. The fixes: guard the getter as well, or better still, finish every state change before you ever hand control to an outsider. The lesson that runs through all of DeFi: a value you can read at the wrong moment is a value someone can weaponize. A quick note, rebuilding these hacks safely and clearly takes real work. If it helps you, the wallets are on screen and there's a Ko-fi link below. Every tip funds the next breakdown. Thank you. Chess is that's read-only reentrancy, robbery pulled off by a single view function, rebuilt and fixed in a few dozen lines. Next episode, price oracle manipulation, how faking one number lets you drain a protocol that trusts the wrong source. Subscribe so you don't miss it, tell me in the comments which exploit to break down next, and I'll see you there.